Hello friends, we've got a wonderful winter morning here and a sexy differential equation to keep us warm. Now, I've got some tea with me, be sure to grab something and let's get into this. So, this is the first differential equation in the series that we'd like to solve because it's leading up to a very interesting one that I encountered in an entrance exam for a university master's degree in mathematical physics. But to solve that one, we're going to need this one and another one. So let's get into it. I've looked at some videos on YouTube on how to solve this. Instructions, obviously, I knew how to solve it before, but they all say that you should form something called a characteristic equation. Why am I writing it down? Yep, a characteristic equation. Well, with this characteristic equation, you're supposed to convert psi into just any constant, and you see how this constant acts, and you put it on the E, and it's kind of all obscure. Papa Flammable Math, he knows that this is a bad explanation, and he solved it by himself with his D. And this is how we're going to solve it today as well, using Papa's D. I think we're going to go a little bit more general, but that's because it's easier to go general than to make more preparations. So what we're going to say first, without any loss of generality, is that, well, okay, first let's say that psi double prime is just d squared psi by dx squared. This is just notation. And then we can define the big Papa's d as d by dx. And rewriting in this format, we can have d squared psi minus k squared psi equals 0. Or, as we can see, that is d minus k, d plus k, psi equals 0. This, of course, we can do because the d operator commutes with a constant, because the constant is non-differentiable, or its derivative is 0. Okay, now that we have that, we don't really see what to do now, do we? Well, let's see if we call this function psi a product of two functions, let's say f of x and another e to the 5x. This might seem unmotivated at first, but since we can do so as long as this satisfies the equality, one of these will be arbitrary, right? So for example, f of x is just psi of x e to the minus phi of x, right? So if I were to choose an arbitrary phi, I could make up for it with my f. If that holds, and let me just mark this equation as 1. If that holds, then let's just plug it in. Let's plug psi in. Of course, one more thing that we'd like. So whenever, in a differential equation, whenever you express one function as, in terms of two new functions, the reason you're doing this is because you want to use one of the arbitrary functions to simplify the problem. So right now, when we put in f e to the phi, we'd like d plus k acting on f e to the phi to simplify to something. Well, let's see what that is. I'm obviously omitting d minus k because d plus k is acting first. Of course, we could have changed the order, but first of all, we're just looking at d plus k. So this d plus k acting on f e to the phi is df e to the phi. This is the product rule, right? Plus f d e to the phi, and plus k f e to the phi. K is just a constant, so it doesn't do anything weird. Okay. So since k is a constant, we could just let k multiply e to the phi as well, like this. And then we can just multiply f in front, factor it out. And since one of these is arbitrary, like I said, why not set this to be 0? If that's 0, then we need d e to the phi plus k e to the phi equals 0. And now obviously we know that d e to the phi is just phi prime e to the phi, plus k e to the phi is 0, and e to the phi cannot be 0 by definition. Nothing e to the anything is never 0, so we will just divide. And we get that phi of x is minus kx. Now I could include plus c, but please notice that e to the phi would then be e to the minus kx e to the c. And this e to the c can just be included in f in the definition. Psi is f times e to the phi. So the e to the c would just be absorbed into the f. So we can hold on to this. E to the phi is e to the minus kx. We know that. Then from 2, we have the d plus k of f e to the minus kx is just e to the minus kx f prime. Okay. Now we want to plug this result, let's call that 2b. We want to plug 2b into a, right? Or, geez, into 1. 1 was the general equation. So we've got d minus k of f prime e to the minus kx equals 0. Now we want to solve this. Well, let's just take the same approach. No one's stopping us from doing that. If I just say now that f prime e to the minus kx is some new function g of x, e to the theta of x. Theta is also new, right? Notice that it's absolutely the same approach. So we've got this one, psi is f times e to the phi, and now this, which is also being differentiated, acted on by this linear differential operator d minus k. We just define it as a function g times e to the theta. And now we could assume that everything is going to turn out the same, but let's just do it step by step anyways. So d minus k acting on g e to the theta is, as we've had, dg times e to the theta plus d minus k e to the theta and g in front, right? And now we again say that we like, okay, let's just multiply that out, d e to the theta minus k e to the theta. Now that we have that, we again say that we want this to be equal to 0, right? Yeah. So we say that we want this to be equal to 0. And if we want that to be equal to 0, we'll need theta prime minus k equals 0, or theta of x is kx. Again, plus c would just be absorbed into the g. So now, this is our whole differential equation, by the way. So this is equal to 0. This statement is equivalent to 1. Equivalent to 1. All right. So since it's equivalent to 1, and it's equal to 0, that means that dg e to the theta is equal to 0. Now again, we know that e to the theta is kx, but even if we didn't, we could still divide with it. And that means that g prime of x is equal to 0, or of course that g of x is a constant c1. If g of x is a constant c1, we just need to look at our definition for g of x. Sorry, I'm a little bit unorganized. So from here, from this one, we express that g of x is f prime e to the minus kx. Let's plug in theta. Theta is kx, right? So we're dividing by e to the theta, meaning we just get a minus. So again, e to the minus kx. See, g is equal to f prime e to the minus kx divided by e to the kx. We could, of course, put this as minus 2kx, which we shall. Now we want to look at f prime. From here we have f prime of x is c1 e to the 2kx. Of course, multiplying both sides by e to the minus 2kx. And from here, f of x, we integrate. This one is a little tougher. Integrating in our heads, of course, like big boys, we get 1 over 2k c1 e to the 2kx plus c2, another constant of integration. Of course, I could label c1 over 2k as just c1. Let's do that. So c1 over 2k, just relabel to c1. And then f of x is c1 e to the 2kx plus c2. Now this should look very familiar to those of you who've solved this differential equation by learning the solution by heart. Because f of x is also, or rather let's express psi of x, which is the one we're looking for, is f of x e to the minus kx. That's what we had from over here. And now we just plug in f, and we get that psi of x is c1 e to the kx plus c2 e to the minus kx. So this is our final solution. And notice that in this step, let's see, this step over here, we had d minus k and d plus k. We could have had d minus a, d minus b, and note that then our solutions would be e to the ax and e to the bx here. So this is a sort of special case of d plus a, d minus a, d minus b. But this is the one we needed to solve. So remember this video, remember the solution, because it is going to be necessary. Let's erase this. It's going to be necessary for our next video. That's all for today. I salute you. I still haven't figured out how to end the video.